Hello everyone and welcome. I'm Xavia, your true solid-state LiDAR. Thank you for joining today's webinar, A New Vision Through Solid-State LiDAR. Our speakers today are Philip Geuns, CEO of XenomatiX, and Nick van den Broek, Software Manager at XenomatiX. During the session, feel free to send us your questions using the question or chat box located on your panel, and all questions will be answered at the end of the webinar. So enjoy the webinar, and I hope you gain good insights into the world of true solid-state LiDAR. Over to you, Philip.
Let me join Xavia in welcoming you to this webinar. We will take a quick start and make best possible use of your time. Following topics will be handled today. First, we will talk about the benefits of LiDAR and more specifically, the benefits of solid-state LiDAR. We will show you different variants of Xavia and the unique features of the products. You will get the entire Xavia experience starting with unboxing. Next, we show you how to interface with the sensor. You will see point cloud data and quality, and we will be discussing possible applications. At the end, there is enough time for Q&A, so drop your comments and questions in the question box during the session. LiDAR is the 3D sensor of the future for a wide range of applications, and this future begins now. Clearly, the strength of LiDAR is the spatial insights it provides. It makes it easy to precisely detect and locate objects. LiDAR is often used in applications where there is relative motion. And based on three-dimensional geometrical data, LiDAR also provides dimensional information and dimensions of detected objects. Based on consecutive measurements of the same moving object, the trajectory of that object can be revealed. This makes LiDAR very suitable for navigation and motion control. LiDAR does not need ambient light, so unlike cameras, it works day and night. LiDAR is not affected by the presence of too much sunlight or the lack of ambient light. And also, LiDAR data is not influenced by shadows or dark areas. Based on this, LiDAR can do very trustworthy obstacle detection and solve many of the shortcomings and corner cases where camera and LiDAR fails. And last but not least, LiDAR can detect humans but cannot identify specific individuals. The resolution of the LiDAR is much higher than radar, but the resolution is not too high to trigger GDPR concerns, unlike cameras. And this makes LiDAR very suitable for security and access control applications. Clearly, these benefits are common to all LiDARs. So allow me to add a few more specific benefits of solid-state LiDAR. The LiDAR we are presenting you today does not have moving parts, no rotating or oscillating mirrors, no beam steering mechanism, and no MEMS. Also, it does not measure point by point. This makes LiDAR very suitable for use on vehicles and moving objects. The ego motion and the vibration in the vehicle will not affect the measurement quality. Also, stitching all the data to express it in the same coordinate system is much easier than for LiDARs that are measuring point by point. And all of this results in very clean and sharp point clouds Xavia is providing. Thanks to the way this LiDAR is constructed, she has also a longer lifetime and does not require complex maintenance. And the solid-state LiDAR we're discussing today offers the same resolution in the horizontal and the vertical direction, which I will be explaining in the next slide. What you see here is a scene that we are observing with two types of LiDAR. The red dots come from a scanning LiDAR, a mechanical LiDAR, LiDAR with 32 channels. And as you can see, there is high resolution in the horizontal direction, and the points are close to each other. But in the vertical direction, there is a larger spacing. Solid-state LiDAR has the same resolution in both directions. That are the blue dots, and these dots have a distribution resolution of 0.3 degrees in both directions. If we zoom in on the cyclists, you can see that the cyclist is only seen by 2 or barely 3 scan lines, so you have to identify that this is a cyclist based on 3 line sections. Whereas there are many more blue points that tell you more precisely the shape of that object, and as such it becomes more easy to identify this as a person or a cyclist. So equal resolution improves detection. Better and more reliable detection is also achieved thanks to the fact that LiDAR provides more dimensions than camera images. The camera just returns a flat 2D image. High resolution and heavy AI is required to detect, for example, humans in such 2D images. LiDAR can do the same job more easily and more quickly thanks to the additional information it has, thanks to the 4 dimensions of our Xavia. These 4 dimensions are, of course, the XYZ, but also intensity. And intensity is based on the amount of laser light that each measurement point returns. Some materials return less light, are more reflective or less reflective, and as such, that 4th dimension helps us distinguishing different materials, which helps with classification of objects. On this slide, you see an example of pedestrian detection on a busy intersection in Tokyo. Actually, the detection is done purely based on the sparse LiDAR data that you see on the left-hand side. We have the XYZ, and you can also see the intensity, and the zebra crossing is visible in this sparse data. Despite the fact that it's relatively sparse, we have very reliable and very accurate detection. The image on the right-hand side is only for visualization of the results. It's a standard grayscale image. We are not using that for the detection. We only use it to show the result with bounding boxes. This solution is what we call 4D AI. 4D AI is much faster than camera AI. We can run this at 50 Hz on a neural network that only has half the depth of an equivalent neural network for cameras. And clearly, these results are independent from light conditions. And we do not only get the classification, we also get the precise location of all detected objects. So let's make it more tangible now, and let's move on to Xavia. We have humanized our product. We call her Xavia. Xavia is a common South European name, and it refers to the English word savvy, which means smart. And you will learn our lady here is very smart. We have 2 variants of Xavia. The one you see now is Xavia 3D. This is the LiDAR only version, pure LiDAR. There's also Xavia 6D. This is the combo LiDAR plus camera. And although we invented this type of solid state LiDAR, we do not consider camera to be the enemy. No, on the contrary, we're big fans of sensor fusion and of the combination LiDAR camera. That's why we have created this combo. The 2 are in the same housing, they're fully synchronized, they're upfront aligned, and they are close to each other. As a result, there is only a small parallax error and there's almost no occlusion. And so LiDAR and camera see the same thing. And thanks to the perfect overlay that we have between the 2 data sets, we know the correlation between points in the point cloud and pixels in the camera image. So for each point in the point cloud, we know the corresponding pixel, and we can exchange and merge data. This slide summarizes the key characteristics of Xavia. First of all, the laser light Xavia is emitting is covering 100% of the scene. So we don't measure sequential points, we don't use partial illumination, we don't have gaps in between lines or points. There is full coverage, and as such Xavia will not miss objects. Also, she's smart, and there is computing power. All the processing of the point clouds can be done inside the LiDAR. Xavia is brilliant, meaning she can deal very well with reflectors. That's an important topic on its own, and I come back on that later on. It's a hard-working lady. She works day and night, again, because of the fact that LiDAR does not need ambient light. You will learn that she has high dynamic range and high measurement range, yet she's only class 1, meaning eye safe. That makes her a classy lady. We have foreseen enough brain to not only do the point cloud processing, but also to run applications inside the LiDAR. That's the next step we will be taking, and there is plenty of computing power. So late in the next phase, specific applications will run inside the LiDAR, and only the result will be given out via digital I/O or in other ways. And then when using this combo of LiDAR and camera, Xavia will see everything, nothing will be missed. And last but not least, she's rock solid, referring to the fact that this is solid state technology. LiDAR and camera sensor fusion gives a lot of possibilities for using and combining the data. Xavia gives you very rich data, and here are different ways of outputs and how to use that output. In the upper left corner, you see an overlay between a color image and the point cloud. And the small colored dots are points from the point cloud with color proportional to distance. We have alignment between both, so we have a perfect overlay. You can use the combined data set for your analysis of the scene. You can also just use the point cloud. And there are different ways of coloring that point cloud. You can do color coding based on distance, on height, or you can do a color coding based on the camera image. So the blue helmet of the first cyclist is also visible in the point cloud simply because we take that color from the camera. Another way of presenting the data is what we call the depth image. It's a two-dimensional way of representing three-dimensional data. So we project the point cloud onto a flat image, and we use color to indicate distance. So in this garage, you can easily distinguish the different objects at different distances. The same scene is also observed by a camera, so you can also use just the camera image for doing detection. But I think you will join me in saying that detecting this person is much more difficult in the camera image than in the LiDAR image. But again, you're free to use both data sets. You can do AI on camera images, you can do AI on LiDAR data and compare the result of both directions to further enhance the reliability of your detection. So sensor fusion is the keyword, and sensor fusion is also shown in this small video. Again, point cloud and point cloud plus camera gives a colorized point cloud. All of this rich data is available to you. We have a few more examples to help you understanding the strength of the Xavia outputs and of sensor fusion. What you see here is a Xavia unit that is monitoring the gate of our warehouse. In this first video, you see the overlay between point cloud and image. Your eyes will of course focus on the image because this is how you have trained your brain. Right? It makes it easy for you to understand what is going on. In the second video, you see only the point cloud. And here we have applied a color coding that is proportional to elevation, and so the height of the points. But still, thanks to the depth information, it's very easy to understand what's happening in the scene. And on top of that, you can not only understand, you can also take measurements from this. You can determine relative positions, you can precisely reveal trajectories, distances, and dimensions, which of course is much more difficult in just camera data. A third visualization is again the point cloud, but this time the color we are adding is a grayscale value that comes from ambient light. So you can imagine or consider this a kind of a 3D image. And then last but not least, again, the colorized point cloud, where each point in the point cloud gets the color of the corresponding pixel from the 2D RGB image thanks to the alignment. Okay, as a next step, let's do the unboxing and have a closer look to how Xavia is delivered and what you receive. And it's very self-explanatory. I'm not going to give too much additional explanations. This is what's inside the box. This is what you receive. So what you see is what you get. On the back side, you have the different ports. There are also some digital IOs. You have the laser safety label class 1. And then in the bottom of the box, you have the corresponding cable set. So a LiDAR unit always comes with the right cable set. We foresee a power cord for your region. There's also the data cable and the triggering cable. So now that we have unboxed the product and we have it here with us, I give the floor to my colleague Nick, who will tell you how to connect it to your computer and how to start using it.
Yes, thank you, Philip. So hello, everybody. My name is Nick, and I'm very proud today to show you how you can work with Xavia. After having met Xavia in person, after unboxing, and she's also presented right behind me, the question is now, how can you work with this product? There are two ways that I'm going to introduce to you today. The first of which is what we call the X configurator, and it's a web app that is always available to you. The web app is an application that is running on the Xavia directly. So it means you don't need to install or download anything. You have to connect the Xavia to your laptop using the Ethernet cable provided in the box. You type in the IP address, and the X configurator will pop up in your web browser. And this will work on any Windows and Linux. The configurator that you see will show you basic information like the IP address, the MAC address, the status of the sensor. There are also the options to reboot or power off your sensor. And it comes packed with useful information like the user manual, like all the SDKs and other resources. They're all available, even in the field. You don't need internet access to do any of these actions. They're always there on your Xavia. Now, an interesting extra feature from this web UI is also an onboard viewer, which is shown in this small video. So the onboard viewer allows you to see the point cloud in the field without any installation, without any access to internet. As Philip explained in the beginning, there are a lot of different ways to visualize the point cloud data because we have a lot of different data sources. So the viewer allows you to choose between different visualizations. What we see here is the two-dimensional view. So as you can see, we have a front view of the point cloud. In this case, in the demo, we have a demonstration point cloud, which is very useful for us as developers to have a point cloud where we know exactly what we should expect to see. It's very handy to find issues. In this case, that is a nice plane at 20 meters from the sensor with our XenomatiX logo in front of it. As you might see here, there has been a drop-down box where you could choose the coloring. So in the beginning, we were calling based on reflectivity. Now we are calling based on the distance from the sensor itself. Red colors means further away. Blue colors are closer by. And as you can see from the video, it's actually moving, which from a 2D view, as the camera sees it, is very hard to see. But in the 3 dimensions, you will immediately understand what is happening. So the XenomatiX logo is waving in front of this wall at 20 meters distance. So the viewer also allows you to look it in 3-dimensional space. You can rotate around it. You can even, if you would like to, view the point cloud from the back. And all of that information is available in the field. The usefulness for this is that when you are installing your LiDAR somewhere in a corner or outside, you can plug in your laptop and immediately see what's going on, which makes it very useful to precisely locate the LiDAR. You also can see the time of the LiDAR and the timestamp of every frame that comes in. Now, this is nice to see what's going on. It will also help you with the installation of the sensor. But what is, of course, very useful from LiDAR is that we want to measure stuff. If you want to measure stuff, and if you want to also use the LiDAR for your application, and we want to use the LiDAR to control whether an object is in a certain location, we want to check how many distance there are, you want to control a gate. There are many, many applications which we will talk about also later. For that reason, we have the SDK. So let me show you now this second way of interacting with Xavia, and that is using the SDK to do the integration into your own products. When we started building this SDK, we actually started building it for ourselves. We really wanted to create an SDK that we would enjoy working with. And one thing that I personally hate is that I have to write hundreds of lines of code just to see the first point cloud coming in. So we built an SDK which is modern in usage. It's very easy to use. As you can see here, these 20 lines of code are the first lines that will simply allow you to run and get the first point clouds. These are all the lines you need to write. And I actually say need to write. What I actually should be saying is that you can copy paste them because these are available already, even runnable as examples in our SDK. Let me walk you through this just a little bit to show you how easy it is. And one line I would like you to focus on is here line 8, where you can see factory build. Factory pattern is something that all developers will immediately understand. So we are using state-of-the-art but standard usage patterns, so that's easy to understand what's going on. But this one line is actually the line that connects to the sensor, gets like the serial number, and makes sure that everything is in order to start talking to the sensor. And then this sensor object, you can manipulate it. For example, here we're calling start and stop. So you see this is very easy and straightforward to read. You don't need a PhD in software, in computing software to understand what's going on here. And that's of course the purpose, to make it easy to read. The other element here is this on new point cloud callback, which is actually the function that you see below. This is an example of how the point cloud comes into your code. So for every line that comes in, you get a reference to this point cloud element, and you can access all the information that is necessary to do any of the applications. But let me jump in a little bit more on this point cloud element, because of course that's one of the interesting things for you as a customer is, okay, what kind of information do I now actually really get? What can I play with in order to solve my solutions? And this is the exact information you will get access to. The first 3 lines show you that you will have access to the X, Y, and Z information. So this is the 3-dimensional scene, the 3D coordinates, as Xavia measures the world. The following information that you get is the measured distance. So this is the distance between your sensor and the object that was measured, which is what we use to do the depth measure coloring, as Philip explained. Reflectivity is a measure for how much of the laser light is reflected back to us. Ambient is a measure for the amount of light that is not from our own LiDAR, but can be from the sun or from an external light source. Confidence is a measure for how confident we are in the measurement. And so as you know, there are physics applied in all cases. Due to some external circumstances, the measurement can be better or worse. It can be more noise or less noise. This confidence will give you, or your AI, insight into the confidence, the quality of the measurement. Very useful for your AI tools. Finally, a few other things like the metadata struct that we have here and the probes struct here. This gives you extra information about the sensor itself. So metadata is about timestamps. When was the point cloud recorded? There are also counters in there, which give you the sequence, so that you always know which point cloud was, when was it in time, and which was the point cloud before, which was the point cloud after that. All of that information is, of course, available from the SDK. The probes are like humidity and temperature, which can allow you to measure the condition in which the sensor is working. Finally, a word about I/O. So, of course, getting point clouds into your application is one thing. The next step is to then use them to do calculations and get some output to steer or control other actors in your solution. But of course, during the development or even in the final solution, it can be interesting to store the information as well. Because you have access to all fields, you can store the information in any format you like. So you can make this sensor fully compatible with your existing infrastructure if you want to. If you just want to have a quick dump, then we offer a serialize and a deserialize function that just allows you to write all of the point cloud without data, without any loss to a disk or to a cloud or to a database. And with the deserialize, you can read them back in, which is also very useful during development so that you can replay your sessions and get back the same information as was originally coming from the SDK. This SDK is available, as I said in the beginning, from the sensor itself. So you can simply download it, even if the field, if you would need that. It uses C++17 and a very modern design with testability and modularity up front, which should allow you to reach a very high quality of code, which is important for the future of your own company. It supports CMake for easy integration. So besides the 20 lines of code that I showed in the beginning, you have to add 3 lines of CMake code to import the library into your own platform. The SDK, the zip file, includes the manual in English, an API reference document, which is kind of a dry explanation of all the functions available, and also importantly, working examples. There are about 7 examples that highlight different parts of the SDK. They all work, they all built, they all come with explanation, all to lower the bar to get going very quickly with this SDK. Normally, we don't expect people to last longer than an hour before they have a working first version of the code with this SDK. Especially because the examples, as I said, they are running, so they can act as a boilerplate. You can copy paste the example and you don't have to start from zero even. With this, you have all the ways to interact with Xavia, and I will leave the floor back to Philippe to tell you what you can do with it now.
Thank you, Nick. After explaining us how to interface, and you also understood what's inside the box. So let's talk a little bit more about the capabilities and the skills of Xavia. And I'm not going to list all technical characteristics. For this, I simply refer to the data sheet, which you can easily access via the QR code on Xavia's ID card. Yet a few characteristics are worth mentioning. Xavia has a field of view of 57 degrees horizontally by 17 degrees vertically, and the resolution is 0.3 degrees in horizontal direction and also 0.3 degrees in vertical direction. The frame rate is 10 Hertz or 20 Hertz. 10 Hertz is the standard, but you can optionally take the 20 Hertz variant if you have a more dynamic application. Clearly, lower frame rate also means lower power consumption, so for you to make the trade-off depending on your application. In terms of measurement range, we have a 10-meter version and we have a 140-meter version. And depending on what variant you take, power consumption will be between 15 and 23 watts. The strengths of Xavia. One of the key elements, of course, is the superior point cloud quality. With other LiDARs, you sometimes have to do some cleaning and polishing. You have to remove ghost points, false reflections, and so on. That is not needed with Xavia. Xavia gives you very clean and very accurate data. In the following demonstration, you will also see the high dynamic range of the LiDAR, and high dynamic range means that she's capable of measuring objects close by, but also far away. And close by really means a few centimeters, and it's almost zero standoff. Xavia floods the scene with laser light. As I mentioned already before, there are no gaps in between the points. Full coverage, and full coverage means also high detection reliability. Another key feature is best-in-class reflector handling, and that is because dealing with the reflector is a major challenge for most LiDARs. And especially for LiDARs that flood the scene with so much laser light, because wherever there is a reflector or a traffic sign, it may blind the LiDAR. That is why we had to develop advanced reflector handling. We have solved this problem. And as a result, Xavia has a very large dynamic range. You can see a a very reflective object close by and at the same time see a very dark reflector far away without any distortion, and there is no saturation, there is no blooming, and there is no impact caused by the high reflective object nearby. Xavia 6D delivers you a perfect overlay between the 2D image and the 3D point cloud, thanks to the pre-alignment between the two. And Xavia also has a rugged design. As you can see, she is wearing a metal dress, and we have treated her very roughly. She has been in a thermal chamber. We put her on mechanical shakers for endurance tests. We have dropped her, we have submerged her. She survived everything. That made her very strong, and she's doing all of this without losing performance. For onboard applications, there is also the possibility to use digital I/O and to make use of an integrated IMU. And Xavia can also act as a bossy lady, being master in a synchronized setup where she gives a trigger out. A few more words on this advanced reflector handling. I think you're familiar with it. If you want to check a LiDAR, then put a license plate or a traffic sign or a reflector close to it. Put a low reflective object in the back and check whether you can see, whether the LiDAR can see both. In case of Xavia, she's seeing both, and the license plate is perfectly measurable, and also the low reflective object in the back can be seen. And this I want to further illustrate with a demonstration that we have recorded. So this is a setup here at XenomatiX with Xavia in the front. And in the back, you see a large white wall, calibration wall, very flat. At this moment, it's at about 15 meters away from the LiDAR. And the other object in the scene is a calibrated or verified target with 10% reflectivity, 10% Lambertian reflectivity. In the top right corner, you see the measurement data from Xavia. So a color-coded point cloud. We show this as a depth image, and the color shows distance to the LiDAR. And then we also have the 3D view on the point cloud. And as you can see, this point cloud is very clean, very sharp, very easy to understand. While Xavia is measuring, we are going to bring in some objects, some people, and show you what Xavia is seeing. When this pedestrian is walking around, you can still see very clean data in the background. Of course, the person throws a shadow on what is behind him, but there is no influence of the motion of the person on the other points. We continue to see a very stable, low noise point cloud, even when the person comes very close by. The fact that the screen turns blue means that all measurement points are now very close by, only a few centimeters, but these are still valid measurements. And as soon as the person steps aside, again, the scene in the background is very well visible. And you can see the person and the low reflective target in the back at the same time. Maybe this was still easy, and we show you just to give you an impression on the quality of the point cloud, but let's crank it up and let's make it a lot more difficult. Now, next to the low reflective target and the person, we will bring in a reflector. A reflector being a traffic sign, and traffic sign actually has a reflectivity of a few thousand%. So it returns the light more focused than the way the light hits the target. Bringing a reflector, a traffic sign, so close to a LiDAR is challenging. And look at the measurement data, it remains very clean. You continue to see the arms and legs of the person, and so very sharp separation between the different objects. And also the target, the low reflective target in the back remains well visible. And we're going even to go to the next level. Let's bring this reflector at a few centimeters in front of the LiDAR, trying to blind it, but that's not happening. You can see the LiDAR, the traffic sign is partially covering the view, but now traffic sign at a few centimeters and 10% reflective target in the back, both are visible, and the point cloud remains very, very sharp. When the reflector is at a few centimeters, we have an homogeneous and correct measurement of points at a few centimeters, and so that's why the color is blue. But again, there are valid underlying measurements. And then the person steps away, and again, the scene in the background and the traffic and the low reflective target become visible. Again, challenging exercise. I hope you can appreciate this. This is the best way of illustrating the very large dynamic range and the high quality point cloud that Xavia is returning. Another slide to illustrate the strength of this advanced reflector handling. This shows a comparison with and without this feature. We have a scene here, an outdoor scene. Where we have a number of reflectors nearby. We have some traffic signs left and right of the road. With advanced reflector handling active, all measurements are correct. Everything is very clean. On the right-hand side, you can see a very clean three-dimensional view on the scene. If we were to switch off the reflector handling, indeed, ghost points do appear. This blue area are objects that are at the same distance as this reflector, but of course there are no objects at that location. These are just false measurements caused by the reflector and not eliminated because advanced reflector handling is not active. Also, in the back you see that the traffic sign is becoming a little larger compared to what it is in reality. So advanced reflector handling contributes very much to clean measurement data. Okay, as a next step, again, a recorded demonstration where we bring Xavia into an outdoor scene. The LiDAR is monitoring a road where traffic will be passing by. It's also monitoring parking lots. We have some trees in the background. The road is at about 40-meter distance. And on the other side of the road, you may recognize again the same low reflective target. So this target is placed at about 45 meters from the LiDAR. And as you can see in the point cloud, it's very sharp. We have frozen the image. We didn't see the car passing by because we want to show you that the LiDAR sees this low reflective target in this very crowded and dense scene. There's a pedestrian passing by at that distance. And you can also see that our color is very stable. Of course, the trees are a little bit moving and objects are passing by, but the individual points tend to be very, very stable and of very high quality. That low noise strength of this LiDAR can also be demonstrated in a different way. We are going to point the LiDAR to the sky. And in the sky, of course, there is nothing, there are no measurements. So we should indeed see that no data is returned. That will be happening here. We point to the sky. You can see the top of the trees. On the right-hand side, you see part of our building. You see the roof of the building, that is a blue zone. But other than that, the sky is clear, so no noisy or no false measurements. We have put the threshold on the data quality high in order to make sure that you don't have to do any cleaning of point cloud data. As a next step in this demonstration, we want to give you a flavor on the resolution of the LiDAR. And to do so, the pedestrian will walk in holding a metal bar of only a few centimeters wide, 5 centimeter narrow metal bar, which he will place in front of the LiDAR. And then he will start walking backwards with that bar. and for you to see how the visibility of that bar continues to happen in the point cloud. So he's entering now, 5 centimeter metal bar, very easy when he's nearby, highly reflective metal next to the pedestrian. He starts walking, and then we continue to see the bar. And actually, the fact that we can see the bar even at larger distance is a result of the fact that we completely fill the scene. At some point, the 5 centimeter bar will actually be smaller than 1 pixel in the field of view. At 40 meters distance, 35 meters distance, actually, a 5 centimeter bar corresponds to 0.1 degree and not 0.3 degree, but still that bar is more reflective, and that's why it's still visible. So we have a sub-pixel resolution as a result of the way we illuminate the scene. Okay, next part is about applications. Xavia can be used for a wide range of applications in various markets. As you understood from our explanation, our focus is on providing you with good quality data from a very affordable LiDAR, so you can do your own application development. Our initial focus is on providing a good SDK, and that gives you real-time access to the point cloud data and the camera data. As of next year, we will start putting applications inside the LiDAR, because as I said before, there is processing power, more processing power than we need for handling the point cloud, and there's also processing power for interpreting the point cloud, for deriving dimensions or measurements or control signals, and then LiDAR also replaces your computer and can be nicely integrated. But for now, the focus is on working with different people on different types of applications. And this is just a quick overview of what is possible with LiDAR and where LiDAR is beneficial. Clearly, there is smart access control, and that means access control based on the size of what's approaching the gate, or direction, or the classification of objects. Based on point clouds, we can do very good navigation and obstacle detection. In agriculture, we can use dimensional information. Crop size can be determined, and when the crop size is lower, more chemicals may be required. In areas where crop size is higher, you can save fertilization. We have our LiDARs active in mining applications for all kinds of safety aspects. That's also a good fit for Xavia. Smart picking, where dimensions and distance are important on cranes and robots, is an area of application. We can monitor material that passes by on conveyor belts to check the dimensions or to measure how much is passing by. LiDAR can be used for quantifying the amount of material in a stockpile, so volumetric measurements. Of course, there is a vast area of intelligent transportation systems with traffic monitoring, with smart tolling based on dimensions. And we can also do a variety of mobile mapping applications and construction site inspection. Surely there are much more for you to help us completing this list. In summary, we believe that crowd analytics is a strength of Xavia, access control and security, all kinds of industrial volumetric and dimensional applications, and then smart city, which of course means detection of pedestrians and other road users. The sensors can be on the infrastructure, or they can be in the vehicles. So clearly also autonomous driving and ADAS is part of the wide range where solid state is beneficial. How to obtain Xavia? There is more good news to share with you. and that's basically the price. Let's face it, probably one of the most important characteristics. Of course, you take it for granted that the point cloud is of good quality. So do we. To be very transparent on price, Xavia can be obtained at prices starting at 2,975 euros. We have the two variants, Xavia 3D and 6D, and you can configure them in line with the needs for your application. Standard, they come with 10-meter range, but you also have the 140-meter range version. Standard, there is 10 Hertz, you can switch to 20 Hertz, and you can also add this advanced reflector handling. For indoor applications, 10-meter and no reflector handling may be sufficient. For outdoor applications, you may need more. And we apply the wide thin principle, so you just pay for what you need and you configure the product that is meaningful for you. And this can actually be done on our website. We have opened a web shop fully integrated in the XenomatiX website, xenomatiX.com. In the menu, there's a category shop, and that brings you to a page where you find all information about the product, and you can configure it in line with your needs, enter your payment and delivery information, and have the Lidar soon afterwards. So that brings it to the end of our inputs for you. If you need more information, we refer to the ID card and the technical data sheet. Also, the other QR code may be very useful for you. What Nick explained is described in a Xavia interfacing document. It tells you what functionality the web UI is giving, and it tells you also about the SDK and its capabilities. So very useful for getting started. For pricing and product configuration, we simply refer to the shop, and if you have further questions, then feel free to contact us or to send an email to info@xenomatiX.com. So that gives us 10 more minutes for answering your questions. My colleagues have been monitoring the question box, and we will have a look at it and provide you with our feedback.
Yes, Philippe. So indeed, we have quite some questions coming in. So there's a lot of interest coming in. I will go through it in random order, and we can see what we can understand. There was one interesting question. What is the IP class of the Xavia?
Yeah, IP class is 67. So it's designed for outdoor use, watertight connectors, IP67.
Yes. We have found somebody who asked, what is the difference between the true solid-state LiDAR and solid-state LiDAR?
Very, very interesting question.
Yes, indeed.
We do not consider MEMS to be solid-state. MEMS is oscillating mechanics. It's micromechanics, but it's still mechanics. There are moving parts. Some people who make a MEMS-based LiDAR give themselves the label solid-state. To differentiate from that, we give ourselves the label true solid-state, and that's something we've now been doing for more than 10 years, so it's not something we invented yesterday.
Exactly. And the fact that we do not use MEMS gives us much more stability in the field, much more robustness, and that's indeed why the true solid-state is there. We have a question, is the sensor suitable for low-range indoor applications?
Yeah, I hope that the videos answered that point. Yes, it definitely is. Of course, the closer the object is to the LiDAR, the smaller the field of view. That's related to the opening angle. But indeed, if you have a parking operation, this LiDAR can also be used for measuring the last few centimeters. So yeah, absolutely yes.
I think the lower limit of the sensor is 4.2 centimeters, which is actually the front glass of the sensor itself.
Yeah, yeah, better don't hit that.
No.
It's Gorilla Glass, but still.
Yes. There's a question, is power over Ethernet available?
Is that one for you, Nick?
That's one for me. So no, there is no power over Ethernet. At this moment, the sensor has two connectors in the back, one for the power, which can work on 12 or 24 volts, and we have one connector for the data, which is the Ethernet connection, but it does not support power over Ethernet at the moment.
Okay, and it's 12 to 24 volts.
Yes.
There is this
Can I say
range.
something
Yeah.
else? Sorry.
Yeah.
12 to 24 volts. Yes.
Mm-hmm.
I have a question here. Does the SDK support Python? I think that's also one for me. The Python SDK is on our roadmap, but currently, no. The current SDK only supports C++ 17 or upwards. We do support different platforms, but not Python at the moment.
Yeah, but stay tuned. It will
It's
follow
on the
soon.
roadmap.
Yeah,
Yes.
it will follow soon.
Yes. I have one question here. Are these results with the advanced reflector handling option? But I don't know when it was asked, so I don't know what these results.
So the advanced reflector handling function is optional. If you have an indoor application or if you don't have reflectors, you don't have to pay for it. It saves you some money for you to decide whether it's relevant, yes or no.
Here we have a question in the walking model video, which is the first demo video that you explained, Philip.
Mm-hmm.
The question states, there is persistence of pixels in the formal location of the reflector. Is that a ghost image function, or was it the ghost image function not active? I think ghost image function, they refer to the advanced reflector handling that we have. Well,
let me try to understand that question, or if you have an answer, Nick, please go ahead.
Yeah, so one thing we can say for certain is there is no temporal connection between consecutive frames. So there is no way that the reflector in one frame can have any effect on the next frame. That's for certain not possible. And that's how I interpret this question, that there was some kind of lagging persistence of pixel in the formal location. I think it's lagging in time that they refer to, but that is not the case. That can never happen.
Yeah.
And as we saw within one frame, and that's the entire power of the advanced reflector handling, the neighboring pixels are not affected by the reflector itself.
Correct.
Which is of course the strength.
The anti-blooming.
Yes. So if you have an application or a use case where you expect a lot of reflector, for example, on the street where there are a lot of cars, then we certainly advise you to buy the advanced reflector handling option. I have here also one. How many LiDAR sensors do I need to create sensor fusion with 360 panoramic camera?
Yeah, I would say at least 6. It's maybe 7 because the field of view is just below 60 degrees. But you have to consider this LiDAR as the equivalent of a standard camera. It's a unidirectional LiDAR. Clearly, there are applications that benefit from rotating LiDARs. We are not pretending that unidirectional LiDAR is suitable for all these use cases, but it's correct that we've tried to make this product affordable enough so people can install multiple ones, can combine multiple ones. Whether you have to use it as an equivalent for a 360 degree, I don't know.
No, indeed. I have one final question. It's quite a technical one. To quantify motion distortion, how long is the 3D sensor acquisition interval for each frame? And then they say excluding other time. So I think they really mean like the exposure time of let's say the sensor. So we have, can I say this?
Sure. Yeah.
We have an 0.9 millisecond exposure time. So it means that the let's say for one measurement, the motion blur is 0.9 millisecond of time, which is very, very fast.
Yeah. Related to that, I got another question, and that's about the synchronization between the LiDAR and the camera. Clearly, they have a different opening time. So LiDAR light is a little faster than a camera typically, but they're synchronized in such a way that the opening time coincides as much as possible. So that also helps with the synchronization between both.
Exactly. And I think with this, we are nearing the end, and I'm through the questions.
Yes, also in terms of time, we are nearing the end. So this brings us to the end, and we want to thank you for your active participation, for your interest, for spending time with us. Again, we hope this gives you new insights, gives you inspiration. If you have further questions, let us know. Information will be distributed tomorrow, so you can further enjoy this and share it also with your colleagues. We remain available and we wish you